using Casco again.
Oh, Costco. I don't Casco.
Oh, Casco. We talked about. I love the Costco guy.
No, the software that you use in physics too.
Yeah, it is. That's my fun class.
I don't want to download that on the computer though. Like I don't mind using it on this computer, but I don't want to download it on my own.
What, Casco?
Yeah.
You don't want to like electrocute your computer?
I don't know what is Pasco?
What's Pasco?
Yeah.
Yeah, good question.
It's a software that runs like a bunch of physics, like models and stuff like that.
Yeah.
For when we do labs and whatnot.
I've never used it.
Probably good.
Never even seen it.
Probably better out.
Yeah.
Yeah.
Life is better.
I guess if we have the 8 labs, I think it's for it.
I mean, really, all we do is
All right. Run a little behind, at least for today. 3 minutes behind, but we're here. It's a nice day, so spend, hopefully, if you're not here, you're outside, and you'll watch this sometime later. And so now we are done with Module 2, moving into Module 3. Nice work. And we're going to look at like creating equations of motion on constrained systems. So we looked at kind of moving parts and some of the inverse dynamics problems of like if I know what motion I want the thing to have, what forces do I need? Now we'll look at the other part of more like typical where we apply a force and we want to see what happens after. Yeah.
Just to be clear, the Module 2 project that's due at the end of today.
Yes. Okay. Yeah. So I guess we're not like done, but we're kind of.
But I have like a little more time.
Yeah, that's true. Yep. But yeah, so I jumped right into Module 3. But was anyone still like working on the project like here with questions? I was forging ahead, but.
So the wrap-up is just like a write-up of our findings and everything. You don't have communication or stuff like that.
It can be, if you want to add pictures, then that's fine. Yeah. Yeah, like if you don't want to use, you can like copy paste into markdown cells, like you can add pictures and stuff. But if you're like struggling to use that, you could create like another document and have like two things, like here's my analysis and here's my write-up on what I did. In terms, I think the underlying question was like, can I still get a good grade without pictures? And yeah, you can definitely get a good grade even without adding images and deeper things. The main thing, at least the main thing that I look for in this project for like when you're talking about wrapping up is like specific quantifiable things of like I wanted a windshield wiper with a large range of motion, and I designed one that now has 120 degrees of windshield wiper motion. It can't move too fast, so with a 1 meter long windshield wiper, max speed is something like 4 meters per second, which is 8 miles an hour. So those are the main things of like practice, like why, because we have like all these graphs and numbers and stuff, but why are they important is really the kind of question that you're like trying to answer here. Does that help a little bit? Yeah.
Is it okay if we write the wrapping up like on paper and submit it like that?
Oh, you want to like handwrite it?
Yeah, handwrite all of it.
Yeah, I guess so. And then just scan it and have 2 documents that way. Okay, yeah. Same thing though, like make sure that you're talking about like what did you get from the analysis? Like, how did the numbers that you created either say, yes, I finished the design, or maybe it's still a work in progress. Like, I was trying to do something really ambitious, I'm not there yet, but with further refinements and further funding, I could like get this thing to another state.
Just a question on the code. In the first code block, what does that F bar statement mean?
This one?
Yeah.
That one, so the way this is all set up is that the main idea is that I'm going to plug in a value of angle 1 and solve for angle 2 and angle 3. And so in order to do that, I need some kind of function that if I give it angle 1, now I have two equations that if they equal 0, then I know, then I plugged in the right angle 2 and angle 3.
And if we go to scroll up to the statement
Yeah.
again. So how come it says sine of A1, but then the next statement for L2 is sine of x of 0? What does that mean?
Yeah, let's, oh, actually, I think, oh, yeah, it's right here. So really what I'm doing is plugging in these constraint equations. So what we did was in class figure out L1, L2 equals L3 dx, like dy, and then L1, L2, all the cosines all add up to that dx. So we're saying, like, if I take 2 forward steps and 2 backward steps, I have to end up at 0. And same thing, like 2 steps up a ladder and 2 steps down a ladder has to be 0. You know. Yeah, thanks for clarifying. And it's kind of weird to see like systems of equations written out this way, like have everything set equal to 0 rather than like get the variables solved for. Like usually we're kind of like, oh, x is the square root of something something log, but we don't have to do that. We got a computer, it'll figure it all. It gets pretty close, within 10 to the negative 16 to the answer most of the time. Maybe 10 to the negative 14 sometimes, but it's good. Yeah, thanks. Other work on project 2? Yeah, I figured if we get a start on homework 3, then we'll have a nice like break, kind of like let the information wash over us, and then we'll come back, do a bit of review, and then we'll knock it out and get into module, like finish up module 3 after spring break. Is anyone traveling Friday? Are you gonna be here? This is like the core group. No, you'll be here? Not here? Not here. The question is, should we just cancel class on Friday? It's spring break, right? It's fine with me. Yeah, I'm not offended. It's like, but I'd rather, yeah, there was one, what did I do? There was something, oh yeah, it was the Friday before Thanksgiving last semester. And when I showed up, it was me and one other person. Because I had said, like, I'll be here, like, come in, we can work on something, but it was just the 2 of us. And she said, like, oh, is class canceled? I'm like, no, it's just us. Like, but we had a nice conversation, like, we got to, like, work on something. So I'll be here, but I'm fine saying, like, let's do some work today, and then see you in a week and a half. Sound good? All right, let's do it. I just realized as I was thinking about it.
I'm not sure what's on that.
All right. So we did things a little out of order compared to like just if you were reading the textbook cover to cover, because I think that the constrained motion is like the important new information, and you don't really need a lot of like differential equations and stuff. Like it's all geometry stuff. It's hard, like it's not easy to do, but it's all based on like geometry, so we didn't need to like get into a lot of calculus and stuff. I like to do that before I come back, like back up and do chapter 2 and 3, because now we can do all sorts of cool analyses this way. Okay, so chapter 3, we're working on document Yukon. Oh yeah. As I leap around my desktop. Huh? Coming? There we go. All right. So first question. In order to build, so all of our equations of motion are all F equals ma kind of equations. So quick review. Again, I know we've done like vectors and Cartesian coordinate stuff, but when we're looking at like rotating reference frames and these kind of things, we have one vector, some kind of like P/Q vector, a 3, 4, 5 triangle in an A1, A2 frame. So what are the components in a B1, B2 frame? So, and quick kind of like intro. Like the cursive A, cursive B, at least for the textbook, that's saying like a coordinate frame. So it has an A1 and an A2 coordinate frame. Cursive B is saying that there's a B1, B2. Yeah, for the most part, we are always going to have orthogonal coordinate systems. So like A1 is always 90 degrees to A2. You could make a weird coordinate system that's like an A1 and a B1, because technically they are they're not completely independent, but they're independent ways of describing where the thing is. It gets confusing, and it's usually not worth the extra effort unless you're dealing with like crystal structures or something. All right, so if I want to say R of PQ is something A1 plus something A2, what are those two somethings? Because this is going to give us like our yeah 3 and 4. Yeah, so that one we know directly, right? just like that. Do we know what the B components are right away? Not yet. Should we know them? Like, are they solvable? Like, is there missing information when we rotate a coordinate frame like that? What do you think? So yeah, so I'm just checking in, like, is this even a solve? Is this a question that we can answer? Not like, do I know how to do it? More, do I have enough information? Maybe. Seems like there's enough information, right? Like it's still kind of a geometry problem. Like I have one right triangle. It's the same hypotenuse, but now it's a different right triangle. Something's changing. So I want to see, I'll look around, like I want to check in and see what you think your process is, and then I'll show you like one way of approaching it, at least. Yeah, so let me check in, see what you're thinking. Process.
So I was thinking we find, like, because the 3 is like horizontal, but
Okay.
B1 is up inclined. So
Yeah.
I think we find that base distance from
Yeah.
B1 and B2, and then we do the same for the vertical distance, and then we'll add up the 2 sets of coordinates together.
Okay. Yeah.
When at first like RPQ equals 3, A1 plus 4 equals. I understand it's like the smaller triangle.
Yeah.
So it's a 3, 4, 5 right triangle. But why is that the same as A?
Oh, so it's like once you have a vector, like a magnitude and direction, it's going to be that vector no matter what. And if I want to represent it in coordinate system A, box there, then the 2 components that make it up are 3 and 4.
So that's because it's because in that A1, A2 plane.
Mm-hmm. Yeah, so because A1 is like that horizontal distance.
So you have like two planes, kind of, but they're the same plane.
Yeah, 2 coordinate systems. One like
Oh, yeah.
that. Yeah.
Since you know the hypotenuse on both sides,
Mhm.
if you take your static triangle and then rotate it by this 30 to this
Yeah.
30, can't you just find the cosine sine
Yeah.
from the hypotenuse and
Yeah.
then rotate an angle?
Yeah. Yeah, you should be able to do something like that. Yeah. Yep.
So your A
Yeah.
is your next one coordinate system.
Yeah, and that'll be like
It's asking you to find
minus that one is your
you
new
can check your B
angle.
and turn it to this.
Yeah.
Okay. B is negative.
Oh,
like
so we should
find
solve for the angle too.
the magnitude of the angle of
QP and we're
the
gonna find
X,
out
Y, and Z that won't be the same
between the
between
coordinate system.
Oh, I see. It'll be like
Then I could just do like cosine and sine.
Yeah, okay.
use 2 different ratios.
Yeah.
With the same hypotenuse.
Yes.
like the angle.
Okay, find the angle.
That angle would have to be like 53.1. So I could add 30 degrees to that. So I think where it is, it's that's the reason why the extra part that's like really
Yeah.
add like 30 to shifted add like person time.
Yeah.
And then I just thought of this now, like I like the bottom just like this.
Yeah.
If like translate that into like that would be the one thing that translates into removing.
Yeah,
right?
yeah.
And then things like that.
The only thing,
Yeah.
I think you're adding, but I think the angle's getting smaller.
Oh.
Like, would it be like 53 minus 30?
Yeah.
But yeah, but same idea.
Yeah.
Because I think that would describe like 30 degrees that way.
Okay. Yeah, I see. What you're saying.
Yeah.
Okay. But then, yeah, my hypothesis they use a Indian angle to like trade.
Yeah, and then you do mine later. Yeah.
53.50.
Yeah.
Yeah, cosine. Yeah, 15 minus 33. Okay.
Probably challenge.
Not sure. That's okay. Yeah. That's why I
Add the C, when you shift the triangles, this stays the same, but you're now rotating it backwards, so that the backwards is not like the.
So it cuts it.
The next projection, so like the back ten.
Okay.
So when we do it that way, like normally when we do like the next projection, we do like the cosine of the angle. So, so the 3 was the, give you like 3 cosine.
Yeah.
It's equal, like your dot product.
Yeah, it's kind of like a dot product.
Yeah. B would be like
Radians.
which was like A1, or B1 would be like A1, or the other way around. A1 is like
B1.
Oh,
B1 has.
Oh, that. Did I use what?
the A's are A.
Yes, you have to divide B1.
I think the way we did it doesn't matter.
It.
I mean, I don't, yeah,
No,
it's
you don't-
45 degrees or.
45 degrees makes it a little.
No, I did it in degrees.
So the answer makes sense.
If it was given in degrees, I use degrees.
Just the way they.
Yeah.
There we go.
That would be original. Yeah. That would work. So you just end up like B1 is vector dot B1. Okay. Okay.
I gotta try. If I know one side, I know, it's just what I call that.
All right, two kind of approaches that I've heard so far. One is like, if we do this. One is like, if I know that vector, I know what its magnitude is. Like I know that it's a unit 5, like 5 units along that 3A1, 4A2 kind of direction. So I could figure out this new triangle as like, so this is 5, so this is going to be like a 5 sine, let's call it alpha, and this is going to be a 5 cosine alpha. And then the main thing is figuring out like what that little angle alpha is, something like that. And like nice like kind of trig problem of total angle is something like 50 something degrees. I always forget, like 53. Okay, 53 degrees. 53 minus 30, and now I've got that smaller triangle. That's one way to do it, and it works. But another way was kind of thinking about like when we say that this vector is 3a1 plus 4a2, one way that we could get like this term is say I want to take rpq, dot it with a1, and that's 3. Like, what is, when I have that like 5 at an angle and I take the dot product, like project it onto an x-axis, the x-axis is 3. And same thing, if I take that and dot it onto the y-axis, that's going to be 4, if I want to say like these are the two components that make up that A direction. But I could use the same process for like a coordinate system B, right? Like if I want the X component in a B system, I could say this is going to be R of PQ dotted with B1. And that one's going to be RPQ dotted with B2, like that. But then I still need like B1 and B2, right? But those we can figure out because we know which direction they're all pointing.
Why do you want to, like, what? Yes.
Oh, like this is, when I have a dot product like that, it's a scalar value. So if I want to write B1 in terms of A1, A2, what is that? Which direction? Because it has some A1 component to it, right? And some A2. So I'm trying to get what is the direction of B1. Yeah. Sine and cosine, yeah. Less? Just like that?
I can't rationalize why.
Why?
I can't like rationalize why you use that.
Oh.
It just looks into, like it looks like it's right, but I don't know why. Right?
Why the cosine and sine is right, or
Yeah.
why?
Yeah, why cosine sine is the move.
Oh, why? Sorry, give me what were
Sorry,
you?
that's super unclear. I don't understand why.
Yeah.
It's like, I could say, and like Mike gave me an idea. It's like cosine of 30 and sine 30.
Mm-hmm.
Which, looking at it, like, oh, that makes sense. I don't understand why we use those.
Yeah, why?
Too small in the triangles. Yes. So you're adding the parts.
So what we've got is like, this is A1, this is A2, and I want to know B1 is something A1 plus something A2. Like, how do I write this new coordinate frame in the frame that I already kind of know a little bit more about. And I'm just gonna write like angle theta there, because it's true regardless of what rotation we use. So if I rotated B1 by 30 degrees, how much did I rotate B2 by off of A2? 30 degrees, yeah. Yeah. So this is also angle theta. That one's for the next step when we're trying to get B2. So I'm trying to figure out how much along the A axis, how much along that A1 axis and how far along the A2 axis I need to go to get to the same place. It's all a unit circle, like it's all one away from the origin, but it's pointing in different directions. So this one's going to be 1 times cosine theta, and this will be 1 times sine theta. Does that kind of make sense? Yeah. Yeah. So now if I want to draw like B2, I have to move in the negative direction. Like B2 is going to have a negative part to it. You see that? Like if I rotate this way, I got to push B2 to the left. So this will be like a negative cosine or sine? Sine. Yeah, like a negative sine theta. And then this one's going to be our and this is true anytime you take one system and rotate it by some amount. Like if I have, and even if it's like consistently moving, I can always get it back into horizontal vertical by saying like that B axis is now a cosine theta and a sine theta. The B2 axis is always negative sine plus cosine. So now, if I want to get this like x component, so now I end up with like an equation, a dot product equation. How do dot products work when you have unit vectors like that?
You multiply each component.
Yeah.
With one of the other vector, and then you add up all the components.
Yeah. So like 3a1 dotted with cosine 30a1, what is that?
3 cosine 30.
3 cosine 30. 3 A1 dotted with sine 30 A2. 0. 0? Nice. 4 A2 cosine 30 A1 dotted with A1. 0. And then 4 A2 dotted with sine 30 A2. 4 sine 30. And now I've got, and the nice part about this is I don't need to solve for like hypotenuse and like try to figure out, is it a positive root, like did I shrink the angle, did I increase the angle? Like I'm just using a formula saying like, I know the direction of V1. Let me just, so in this case we're like projecting the vector onto the axis that we want.
Sorry, could you repeat that for like why do people? Because I know dot product is just we get a scalar value. So then you're taking the value calculated and assigning it to people.
Yeah, so this is like my
Oh, because the 30 degrees we're comparing to.
like if I call it bx and by, that's my bx term. So what do we end up with for like our by component? What does that one end up being? Yeah. 3 sine and the sine cosine. What do you think? Are you trying it this way? Or
You move biggest.
I think though for this one, we just use
Oh, okay.
Yeah.
Because routine it backwards.
Yeah, but
Not necessarily.
Yeah, like project, like whenever you're
yeah.
for the most part, that product.
Yeah, I was projection, but I wasn't exactly sure what we did to get there.
Okay. Yeah, just immediately jumping from projection.
Well, it could be a negative value, still be net positive.
Oh,
Because you do,
yeah.
I don't know.
Yeah, it's like,
That was my realization. Yeah.
yeah, instead of like trying to like draw like in every single case, like, especially like if you have like a million elements, you can't like do like the whole like triangle thing every time. So
Yeah.
you just make it a dumb product and you make the integration.
Yeah. Yeah, now you get like actual equations of things that are more generalized.
I feel like
Yeah, do you get the same number?
I'm gonna check.
Well, so like,
Yeah.
part of it's positive, part of it's negative.
Okay.
So I don't know.
Yeah, it should be. No, I know, but the number.
Actually, I don't know how to.
Yeah.
Oh, wait.
I mean, you can put your numbers B2 as negative sine theta A1, which is A2, one of them sine. That's how we define B2. Because B2 is going to the left, whereas A1 is going to the right. So we need the negative sine.
What? I think, so the reason is like, even though this is sine, this is the x component, and the reason it's negative is because we went to, what was it, quadrant?
Yes.
Because we went from quadrant one
Oh,
to quadrant two. I didn't understand when you first used it, so I kind of didn't know.
It's all
You should still ask him how to explain it. You just like to try to this one's like more universally applicable, which is nice.
Yeah, negative 3 sine 30 plus 4 cosine 30, kind of like that.
Yes.
Yeah, I know there were like two approaches. They should be the same number. Yeah, like it, again, within round off error, like you lose a few digits as you do like inverse tangents and plug it back into cosines and sines, but you'll get there. It'll be the same. But I guess the main thing that I wanted to kind of say here is like, you can always write a unit vector in a different coordinate system, right? Like this B1 and that B2, if I know what angle it is, I can always kind of rewrite how things are. So we can always get back to some like known reference frame or convert from one frame to another. Yeah, so whether you think of it as like projections onto new systems or you're thinking of it as like a rotation of a vector. Again, then how many linear algebra people? Some linear algebra. Have you seen rotation matrices? What do those look like?
2x2?
Yeah, 2 by 2. Sometimes, yeah. Yeah. So like rotation matrices look like this. So if I want to say like, hey, I have a vector and I want to rotate it, I can plug it in here and say magnitude is 1.
But I just gonna say that if you evaluate the matrix, it's gonna be cosine squared plus sine squared, and then 1. I think you have a different thing.
Like taking all the work that we just did is bx was 3 cosine plus 4 sine. By is negative 3 sine plus 4 cosine. So like now we can think of like rotating from one frame to another is the same thing as like a rotation matrix of a vector.
I guess it's like, so that first one you solve R, if you evaluate, you get cosine squared theta plus sine squared theta.
You mean if you want the determinant of it?
I don't know, I haven't taken linear out.
Yeah.
You know, like, when you have it, you do like that first diagonal and the second diagonal. Subtract it, it's like, what's that, cross product?
That
I don't know what I'm
one.
talking about. You can get one.
Yeah, you don't know what you're talking about.
No, but I'm honest on that.
Do you remember the determinant where you take the, what is it? You multiply from
Yeah.
top left
Yeah.
bottom right, and then
That's what exactly
subtract.
what I'm saying.
And then
you get
subtract.
one.
And you get 1. Yeah. Yeah, so the determinant of a rotation matrix is always 1. Yeah.
I'm looking for the cosine.
Yeah.
Does that mean that like when we're rotating it, we're not stretching it at all because the determinant is one?
Yeah, exactly. So, like, if you have a rotation matrix that determinant is not 1, like if it's 2, then as you rotate, you stretch it. But here, if the determinant's 1, then every time you rotate by an angle, you end up in the same like magnitude, but pointing. Yeah, your components are just pointing in different directions. Yeah. Anyway, it's the same thing that we just did. It's just now it's all one equation, and all rotations kind of look like this: cosine sine, negative sine cosine. At least in 2 dimensions. In 3 dimensions, now we've got like thetas and phi, like 2, maybe even 3, but we'll deal with just planar stuff for now.
I was talking about differential equations that say like the rounds, it's like your functions are cosine and sine. That's the first row, and the second row is the first derivative, which is,
Oh,
I
for
guess like coincidentally what that is.
yeah.
Yeah, it is.
Yeah, this does happen to be derivatives. Yeah, and that part's kind of weird because derivative of one vector ends up 90 degrees. Yeah, anyway, we'll get to that as we start looking at like cylindrical coordinates. Because if you take the derivative of a radial vector, you end up with a tangent direct vector. Cool. This is a fun way to end. And then we'll come back refreshed after spring break. No class Friday, sounds good? No qualms? All right. If there is anything that comes up for Friday, you can always reach out. Like if you're here anyway and you wanted to talk about something, then let me know. If not, enjoy.